Hello everyone. So welcome to my YouTube channel Zenith GATE Mechanical. So in this session I will talk about the solutions for those problems which came into the GATE 2026 mechanical paper. Okay. So first I will start with the theory of machine and then we will move to the different subjects. Okay. So this is also a 1 marks question from vibration. In a single degree of freedom vibrating system with only viscous damping, the critical damping coefficient they have given and the damping coefficient also they have given. Logarithmic decrement you have to calculate. Okay. So the logarithmic decrement formula you already know, which is nothing but 2 pi zeta square root of 1 minus zeta square. This is nothing but the logarithmic decrement. Logarithmic decrement. What is zeta here? Zeta is the damping ratio. Zeta is the damping ratio. So zeta is the damping ratio. It can be written as C by Cc. What is this C? C is basically is called as a damping coefficient, and this subscript which we are using as a C, this is nothing but critical damping coefficient. So C is also given and Cc is also given. Let me check what is this value, 35, and this is 350. So once you will solve, you will get a 0.1 is nothing but the damping ratio. Okay, which is nothing but the damping ratio. So logarithmic decrement you can calculate. 2 pi zeta value is 0.1 square root of 1 minus zeta square. What is zeta? 0.1 square. 0.1 square. If you solve, you will get the answer as 0.63. Okay, that means the option A is the correct answer. Option A is the correct answer. Okay. So one more question they have asked from the vibration, so in which you have to calculate the natural frequency. I would say this is a very good problem. In the GATE 2026 paper they have asked. So till now, whatever the question which I have discussed, they are moderate level questions. Now this is the one of the best question I would say from the theory of machine. So let's try to solve this problem also. 5 kg mass is suspended at the free end of an overhanging massless beam. Okay, so you have a beam, fine, which doesn't have any mass. So they have clearly mentioned massless beam, and at the end there will be a block having mass is 5 kg, which is suspended, okay, at this particular free end, and having a pin support. Okay, now you can see this here, there will be a pin support. Pin support means there will be a two reaction, horizontal and vertical, but as there is no horizontal force which is acting, so you can assume it is a zero only. Now the second thing is roller support. Roller support is there will be a vertical reaction. As shown in the figure below, Young's modulus of the material which is given as 200 gigapascal, and the area moment of inertia of the beam is 10 to the power of minus 8 meter to the power of 4. The natural frequency of the beam in radian per second you have to calculate. So you have the four options. Option A is the 10, and option B is 10 by 3, option C is 5, and option D is 20 by 3. Okay, so how you will approach in this particular problem? Now, first of all, you have to calculate the reaction. Okay, so what we will do, as you know that there will be one reaction here. Let us suppose this is A point, this is B, and this will be C. Fine. This is nothing but RA, and this will be RB. Fine. So as you know that for solving this particular problem, so you have to calculate the deflection. For calculating the deflection, you need the strain energy expression. Okay, for strain energy expression, that means if I will write the deflection, if I want to calculate that at the C, which will be partial differentiation of the strain energy divided to the partial differentiation of strain energy with respect to the point load P. So let us suppose one point P load which is acting here. Okay, at this particular end, P load which is acting here. Now, what is the data given? The Young's modulus they have mentioned as a 200 gigapascal, which is nothing but 200 into 10 to the power of 9 Pascal. Mass moment of inertia, let me check what they have given, 10 to the power of minus 8 meter to the power of 4. Can you calculate this EI value, which is nothing but the flexural rigidity? Okay, so once you will multiply, what you will get, 2000 Newton meter square. Okay, because this Pascal is Newton per meter square and this meter to the power of 4, then you will get the Newton meter square, and 10 to the power of 9 and 10 to the power of minus 8 is 10, only 10. So if you multiply with this 200, you will get the 2000, right? Now, the mass which is given as 5 kg. Okay. So if you want to calculate the natural frequency, what you have to do, you have to, you know already the natural frequency is K by M, where M is the mass and K is the stiffness. For getting the stiffness of this complete, we can say that beam. So what you will do, first of all, you will calculate the reaction. So if I will take the moment about B point is 0. So summation of moment about B point is 0. So can I say RA into 1 is equal to P into 2, P into 2, fine. So RA value you will get as 2P. RA value you will get as 2P. Now, that means the reaction at A point you have calculated. Okay, so the reaction at A point you have calculated. Now what we will do, first of all, we will calculate the strain energy, because this particular, for getting the deflection, we need the partial differentiation of strain energy with respect to the load. So first of all, we will calculate the total strain energy of this beam. Okay, so if I want to write down the expression for the portion AB, so let us suppose I have taken a section X at a distance of X from the point A. Now for the portion AB, so let me take this diagram so that it will be easy for you. Okay, so for portion AB, suppose if I want to write down the expression for the moment at the section XX, so can I say, which is nothing but RA into X. What is the RA value? 2P. So that means 2P into X. Now, if I want to partially differentiate with this moment with respect to the load, so what you will get? 2X, because you know that the partial differentiation of strain energy with respect to point load for the portion AB is nothing but mx del mx divided by del P divided by Pi. Okay. Now, so mx value you already know, 2px, and the differentiation you have done 2x into dx from 0 to 1, and this EI value is nothing but 2000. So EI value is 2000. So once you will solve, what you will get? 4p, and x square dx integration is x cube by 3, and if you put the upper limit, that means 1 cube divided by 3, and another will be the lower limit is 0, so there is no use. So 4p divided by 2000. So what you will get? So you will get as p divided by 1500. Okay, so you have calculated the portion AB strain energy partially differentiating with respect to point load. Why we are doing this? Because we want to calculate the deflection at the C point. Once you know the deflection at the C point, so you can easily calculate the stiffness. Now, for the second portion, let me take the same diagram in the next slide. Now, what I will do, I will take the section XX at a distance of X from this CN, because I am calculating the strain energy for the BC. So for portion BC, so what is the moment at X? Moment is nothing but this force into this distance. So can I say is equal to Px? If I will differentiate this, what you will get? I will differentiate with respect to P, what you will get? X. Now, the partial differentiation of strain energy with respect to point load for the BC is nothing but, again, mx del mx divided by del p dx divided by ei. Okay, so from where to where you have to integrate? So now you have to integrate from the x is varying from 0 to 2. For this BC length, the x is varying from this 0 to 2. But in this case, AB, you will see I have integrated from 0 to 1 because the x is varying from this 0 to 1. Now here will be the upper and lower limit is 2 and 0. Now, once you will solve this px and this is x dx divided by 2000 and this is 0 to, so x square dx integration is x cubed by 3. And if you put the upper limit, so can I say this value is p into upper limit is 2, so 2 to the power of 3 divided by 3 into 2000. Okay, so I have done nothing. So you just take this x square dx integration is x cubed by 3 and put the upper limit as 2 cubed by 3 and lower limit is 0. So 2 cubed by 3 is this one and this is p and this 2000 will be here. Fine. Now the partial differentiation of strain energy for the p for the portion BC is nothing but p divided by 7500. Now if I want to write down for deflection at the C, can I say this is p divided by 1500 plus p divided by 7500 is equal to p divided by, once you will take the LCM, you will get p divided by 500. That means deflection at C is equal to p by 500, and you know that force by deflection is nothing but the stiffness only. So what you will get? 500 Newton meter. So what is this value? This is nothing but the K only. So I can say this is nothing but the stiffness. Okay, and you know that the natural frequency, I have already told you in the beginning. So the natural frequency is nothing but square root of K by M. So mass basically already given, which is nothing but the 5 kg. And the stiffness you have calculated as 500. So what you will get? Square root of K by M. This is nothing but 500 divided by 5, which is nothing but 100. So what you will get? 10. Okay. So that means option is the correct answer. Option is the correct answer. Okay. So now you can see here the correct answer for this particular question is option A.